Welcome to an exploration of the extremes of material science. Today, we are investigating a substance that blurs the line between the ethereal and the physical. We are looking at aerogel, the world's lightest solid. It is a material that looks like frozen smoke, feels like styrofoam, and possesses properties that seem to defy the laws of physics. Join us as we uncover the secrets of this ghost-like solid. So what exactly is aerogel? Fundamentally, it is a gel that has been transformed by gas. Imagine a bowl of gelatin dessert. Now imagine removing all the liquid but leaving the solid structure perfectly intact. In aerogel, the liquid component is replaced while retaining the solid structure with minimal mass. The result is a material that is comprised of 90 to 99.8% air. It is almost entirely air, trapped within a nano-sized porous framework. The story of this material begins with its discovery in history. We travel back to 1931 and meet Dr. Samuel S. Kistler. Interestingly, this space-age material was invented through an experimental wager, a bet with a colleague. The challenge was to see if the liquid in a jelly could be replaced with gas without causing the jelly to shrink. Kistler won this bet by developing a revolutionary supercritical drying technique. This was the breakthrough technique enabling liquid removal without shrinkage. To understand its properties, we must look at aerogel's unique structure. It is not a solid block, but rather a 3D interconnected nanopore network. Think of it as a solid foam with an intricate three-dimensional architecture. Specifically, it consists of a microscopic silica particle framework. The pores within this framework are so small, smaller than the mean free path of an air molecule, that they trap air in place. This structure explains why it is called the lightest solid. If we look at the density formula, which is mass divided by volume, aerogel achieves an incredibly low mass due to its air-filled structure. In fact, some formulations are only 3 times denser than air itself. It is the minimal solid material present that creates this extraordinary lightness. How is such a material created? It begins with the sol-gel process. Step 1, known as the sol. This is a colloidal particle suspension where silica precursors are dispersed throughout a liquid solvent. These are chemically reactive particles. At this stage, these particles begin linking together through molecular bonds, starting the journey from liquid to solid. The process continues with sol-gel process. Step 2, known as gelation. This is where a continuous 3D network formation occurs. Through condensation reactions, the particles create an interconnected solid structure. The result is what scientists call a wet gel, a porous solid framework that defines the aerogel shape, but at this stage, it still has liquid-filled pores. Now comes the challenge: capillary forces. If you were to let this gel dry naturally, surface tension would cause structural collapse. Simple evaporation pulls the solid walls together catastrophically. This results in a dense, non-porous glass. This massive shrinkage creates a material known as zerogel instead of aerogel. To avoid this collapse, Kistler developed the solution, supercritical drying. By bringing the liquid to a supercritical fluid state, we eliminate surface tension entirely. This occurs above a critical temperature and pressure, where the substance exhibits both gas and liquid properties simultaneously. This allows the liquid to be removed without collapse, meaning the gas phase removal preserves the delicate porous network intact. The resulting material possesses the properties of low density and high porosity. It achieves a minimum density while being 99.8% air. The internal surface area is mind-boggling. Just 1 gram of this material has a surface area equivalent to several football fields. This maximum porosity and open internal volume provide its extraordinary lightness. This structure also grants the material a property of superior thermal insulation. Because the nanopores are so small, They suppress convection currents within the material. This makes aerogel the best solid insulator known to man. Its sparse structure also minimizes conduction, stopping heat transfer dead in its tracks. These insulation properties have found a home in the stars. In application, NASA and space exploration, aerogel is used for Mars rover component insulation. It protects delicate electronic instruments from the extreme temperatures of the red planet. It was also used in the Stardust mission for particle capture, where it gently collected high-speed comet and interstellar dust without damaging the samples. Back on Earth, we see application building insulation. Engineers are developing high-performance construction blankets made of aerogel. These provide superior R-value thermal resistance compared to traditional materials. This technology allows for ultra-thin, efficient wall systems, offering space-saving solutions with exceptional insulation capabilities. The massive surface area of aerogel is also utilized in application chemical cleanup. The porous structure provides massive surface area for absorption, making it excellent for petroleum product cleanup in oil spills. Furthermore, we utilize carbon aerogel supercapacitors, which serve as high-efficiency electrodes for energy storage. There are several varieties of this material. First, we have types silica aerogel. This is the original and most common type. It appears as a white, translucent, brittle solid derived from silica. It is the thermal insulation champion of the family, best known for its exceptional heat resistance properties. Next, we have types carbon aerogel. In contrast to silica, this is a black, electrically conductive material. It is chemically inert and derived from organic polymers. Its conductive nature makes it perfect for fuel cells and electrode applications, as well as deionization and energy storage systems. A third variation is types alumina aerogel. This features an aluminum oxide composition. It is prized for its exceptional thermal stability at extreme temperatures. This robustness makes it suitable for catalysts and ballistic armor, serving in high-performance protective and reactive applications. Despite its amazing properties, there are commercial challenges. The primary hurdle is the supercritical drying expense, which makes production costly. Additionally, there is the issue of silica aerogel brittleness. It can shatter easily. Handling it also creates hazardous fine silica dust, requiring careful safety protocols. Scientists are working to overcome these issues through future research, flexible aerogels. This involves composite aerogel development, specifically embedding the porous structure within flexible polymers. The goal is to create a material that is flexible yet highly insulating, opening the door for durable clothing and construction applications. In summary, aerogel is a material of extremes. It is the nanostructure that defines its extraordinary properties. The combination of the sol-gel process and supercritical drying creates a unique material that stands as a testament to the power of materials science. Its air-filled network delivers unmatched insulation and lightness, forever changing how we view the solid world.